Hello, physics students. We are going to be looking at Newton's third law today. At this point, you should know Newton's first law. An object in motion tends to stay in motion. An object at rest tends to stay at rest unless an outside force is acting upon it. You should also know Newton's second law, which was the equation force equals mass times acceleration. Newton's third law is a law where most people can say it, but they don't really understand how it applies to things. So if I just do this, I'll bet right now most of you could probably finish Newton's third law. For every action, there is an equal and opposite reaction. So I'm going to go through some examples of how that really truly applies to like a real world thing. For example, if I click on walk, that will take me to this wonderful video I found about 10 common mistakes for walking your dog.
Do you want to learn how to avoid these pitfalls?
So if you look, I could refer to this as what are the forces involved when you are a human walking as well. We could be talking about the dog or the human. And in this case, if you look at what it takes to actually walk, it's what I want to do is try to define what direction does the dog have to push in order for the dog to walk forward. So for a person or a dog or anything that's walking, running, what direction do you have to push? If they push down on the earth, well then that would cause them to move upward. If they push forward on the earth, that causes them to move backwards. So if a person, like this person right here where their toes, they're actually pushing backwards on the earth. And when that person pushes backwards on the earth, well, it's the earth then that's going to actually push forward on the person. And it's the reaction force of pushing forward on the person that gets us to go somewhere. So for the dog, the action force is the dog pushes backwards on the earth. The reaction force is the earth is going to push forward on the dog. Let's just try some other examples just to see how it goes. Here's a really awesome video that I found of a kid. He's got some super cool balloons. Here you go. Everybody loves kids.
Whoa!
That's a car toy.
What is that?
It's rocket balloons.
Rocket balloons.
Yeah.
So you're supposed to air them up and then shoot them?
Yeah.
Rip it open. Cool. It's a lot of balloons.
Yeah.
Let's pull them up. What color do you want me to use?
So they slow this one down here. There we go. We'll try to get it as clear as we can. So here's the balloon. What's the action force? And what is the reaction force? Well, in this case, the first thing that has to happen is the balloon has to push the air out of the balloon. So balloon pushes air. Because the balloon pushes the air moves out the back. If you've ever done this, you put your hand at the back, you can feel it. And the reaction force is the air pushes on the balloon. So because the air is pushing on the balloon, that makes the balloon fly around the room, and the balloon moves forward. So what you get is you have two different forces, and because you have two different forces, you have two different motions. The balloon pushes the air, that causes the air to move. The air pushes the balloon, that causes the balloon to move. And then the balloon flies around the room. Let's take another look at action versus reaction forces with a rocket blasting off. I went to one of my favorite guys, Elon Musk, and he is launching the largest rocket in the world at SpaceX. So here we go.
SpaceX has launched the most powerful rocket in the world.
So I'm going to leave it right there. There's my rocket. This is what it's doing. How does a rocket get up into outer space? Does it push on the ground? Does it jump into outer space? What is actually happening in the case of a rocket? And in order to understand what's happening to a rocket, I'm going to refer back to what we just saw with the balloon. See, what you have happening in a rocket is a rocket's a very solid machine. And because that rocket's this really solid, rigid-bodied machine, when you burn that fuel on the inside, that fuel, well, as the temperature goes up, the volume goes up, the fuel expands. Okay? So what you have is the rocket body pushes the fuel out of the rocket. So the first thing that happens in the case of a rocket is the body pushes the fuel out. The rocket's not like pushing on the ground. The rocket's not jumping off the ground to get into outer space. It's pushing the fuel. And then what's your reaction force? Well, your reaction force is the fuel pushes on the rocket. And if the fuel pushes on the rocket, that's what actually pushes the rocket forward. This is why rockets work in outer space. If you're in outer space, you don't have any ground to push off of. The rocket itself, the rocket burns its thruster. And when the rocket burns its thruster, well, the rocket body pushes the fuel. That causes the fuel to move. Even in this video, you can see all this fuel here moving. The rocket pushes the fuel, and the reaction force is the fuel pushes the rocket. That's why the rocket moves. That's how the rocket gets into outer space. It's because it gets pushed by the fuel. Let's go back and look at some other examples of Newton's
SpaceX's Falcon
third law, and another example of Newton's, so just a simple sprinkler. This is something that I saw, found this on YouTube. I'm just going to let it play here for a second, let it spring. I'm thinking about ordering one of these for my yard because it was like super
With
cool.
Orbit's innovative, corrosion-resistant decorative sprinkler, you can water and decorate your yard or garden in style. The rings on the decorative sprinkler spin in opposite directions and come in 3 beautiful designs. It has...
So I'm going to try to stop the video here where maybe we can kind of see what's going on as it spins around. There we go. That's perfect. There's a ring right here. I'm going to drawing tools out here, and the ring is right here. Okay? And you can see clearly that what's happening is I can see water is being pushed in this direction. So the question, what's pushing the water? Well, the sprinkler pushes on the water, which that causes the water to go flying. So the sprinkler pushes on this water, that causes the water to go flying. The sprinkler pushes on this water, that causes the water to go flying. And as a result, we get a reaction force. The water pushes back on the sprinkler. So that little sprinkler part that I'm looking at right now, that sprinkler part is actually moving in this direction. Now, we're not trying to necessarily analyze like which way things are going. We're more interested in analyzing what's the action force and what's the reaction force. In this case, the action force is the sprinkler pushes the water. The reaction force is the water pushes the sprinkler. So you get something that looks like this one.
And is mounted on a stable 4-spike tandem base.
You can see
The
these
decorative
three,
sprinkler covers an area of up to 30
three
feet
right
in
here.
diameter
That's
and
why
can
it's spinning this way,
easily
because
move to
these
any
three are
location
pushing
in
the
your
water.
yard.
If
With
I stop it
60
one more time, these three right here, the sprinkler pushes the water to the right. The water pushes the sprinkler to the left. Super simple design. It's just copper, and it's I kind of like this thing. I might order one of these. Let's look at a couple other examples of Newton's third law. Oh yeah, this is an awesome one. Classic Crazy Daisy sprinkler for your yard from when I was a kid.
When it gets hot, kids need water. No, lots of water. Lots of water, lots of wiggle, lots of squiggle, lots of giggle. Crazy Daisy. Crazy Daisy's gonna get you, Crazy Daisy.
And I'm just going to try to find a good spot to pause it where we can see maybe what's going on in the video and talk about it a little bit. This one might be easier to do in standard here. In that case, the kid is holding on to it, but let's pretend the kid isn't holding on to it. What's going on with the Crazy Daisy in this case? Well, it's very similar to the sprinkler that we just talked about. The action force is that the hose pushes the water to the left. And because the hose is pushing the water to the left, then what you get as a reaction force is the water pushes back on, in this case the Crazy Daisy or the hose, to the right. So the hose pushes on the water to the left, the water pushes on the hose to the right, and we could talk about the motions, but I'm just trying to identify those action and reaction pairs with you. And if that's what we're trying to identify, let's try to stick away from the motion. Everybody wants to talk about motion when we do these things. I'll just show you one more. And this is called Hero's Engine. It's brought to you by the MIT Physics Department. And it's an example of the first steam engine. So he's going to put some water in here. I'm going to skip ahead in the video a little bit. All we're doing is we're adding some water to the Hero's engine. We put our water in. There's a little stopper that's going to screw into the top of it. And then we're just going to start heating this up. Same thing as the rocket. When you heat it up, the water is going to heat up. The water is going to expand. So, what actually is the action and reaction pair here? You can see the steam coming out. You try to catch it right at the beginning here when it first starts moving. There we go. So this thing wants to, that steam is expanding inside there. The water turned into a gas. The gas is trying to expand. So the first thing that you have is the structure pushes on the gas. The structure pushes on the gas. As a result, the steam pushes back on the structure. And what you get because the structure, because Hero's engine pushes on the gas moves off to the right. And because the gas pushes on Hero's engine starts spinning to the left. And you can see it on here it goes, off it goes. So the simplest way that you can write an action and reaction pair, and this is kind of how I want you to phrase them when you're doing your homework and stuff, is the easiest thing that you could write is dog pushes on earth. If you include a direction, that's fine. But keep these, we don't want to talk about things moving. We don't want to talk about things that are in motion. In the case of the dog walking, dog pushes on earth, earth pushes on dog. That's the simplest way you can write it. So what I have here on the next page is I have a couple of ones for you to do. Let's say you're swinging the bat at a ball. And if you're swinging the bat at the ball, I want you to try to identify what you think the action force is. And then try to identify what you think the reaction force is. And I'm going to look at your answers and grade those and give you some feedback in the video. You might want to check back on that, but do that right now. Let's do the same thing with maybe this example. This is a hard example, but this is a hovercraft, otherwise known as the hover pod. And when they fill it up, you'll notice that it's just kind of gliding on the earth like this. What causes the hover pod to kind of glide the way that it does? What pushes on what? I'll give you an idea. Think about the rocket example. So in order for this thing to float, what kind of makes it float in the air? We're not talking about back here. I want to talk about like what makes it float. Okay? And then as a third example, let's take a look at me doing some push-ups. So obviously you guys can tell this is clearly me. I mean, why wouldn't this be me? So here you go. In order to do these push-ups, what is an example of what's the action force? And what is the reaction force? And I do this as part of my morning daily routine. You know, when you get up in the morning, that kind of a thing. Got to do, 100, 200 of those every day. Getting back over by the notes here, so here you go, one last video for you to watch. And this one's self-explanatory, and it'll kind of round us out here on Newton's third law.
There
there are a lot of misconceptions out there, and this is a video about one of the most common ones. So I went around asking people, what makes the moon go around the Earth? And they told me,
the Earth puts a gravitational force on the moon.
but does the moon put a gravitational pull on the Earth?
Pull on the Earth, yes it does. Hence we have tides, etc.
The moon pulls on the Earth too. It affects like the tides and women and stuff. It does. Very powerful.
Does the moon pull on the Earth? Probably that as well, yeah. So what I want to know is, how does that force that the moon exerts on the Earth, how does that compare in terms of size to the force the Earth exerts on the moon?
Well, I'm no scientist, but I think that one would be more powerful than that one.
It's got a greater force coming from the Earth because it's greater mass.
Because the Earth probably has more mass.
Because it's a bigger mass. I thought greater mass is more force.
Does the moon pull on the Earth?
Yes. But a lot less.
Yeah, not as much as the Earth pulls on the moon.
Yeah, but a little bit.
Not very strongly.
Yes, but much, 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 much smaller.
Because of its
Well,
mass.
less size.
Because it's smaller, it's much smaller than the Earth. Because it's smaller. It's small.
Allow me to let you in on a little secret. Everyone got it wrong. The force that attracts the moon to the Earth is exactly the same size as the force that attracts the Earth to the moon. So what's going on here? Why did everyone get it wrong? Well, I think it comes down to cause and effect. The effect of the force on the moon is quite clear. The moon goes in circles around the Earth. But the effect of that force on the Earth is basically negligible. The Earth barely wobbles at all. So people interpret this negligible effect as indicating there's very little force affecting the Earth. But that is forgetting the third key piece of the puzzle, which is inertia. Inertia is the tendency of mass to maintain its state of motion. Since the Earth has a greater mass, it has a greater inertia, and so even with the same amount of force on it, it doesn't accelerate that much. Now the funny thing is, many of the people I interviewed could state Newton's third law, which is every force has...
Oh, an equal and opposite reaction.
Something about Newton's law doesn't seem to fit into that. You're good at this.
Which Newton's law are we talking about?
The whole equal and opposite force thing? Yeah, that one?
So tell me what you're thinking now.
Well, one would think that if the Earth is putting a force on me, I would be putting an equal force upon it.
So why didn't they apply it to this problem? Well, I think they may have memorized the words, but not really believe Newton's third law in their core. Did they really feel it in their spleen? I don't think they did. So, allow me to try to convince you, all of you, spleen included, that Newton's third law really is true. Let's consider two objects. Initially, they have the same mass, 1 kilogram each. So obviously, the gravitational force of attraction must be the same on both of the objects. Now let's add a second kilogram to the first object. The force on the second object will now be twice as great because that 1 kilogram is attracted equally to each of the kilograms in the first object. But what is often forgotten is that new kilogram is also attracted to the second object, meaning that the total force on each object is still the same. They're attracted to each other with an equal and opposite force. We could add a third kilogram, and we would find the same thing. The force on both objects is still the same, even though the object on the left has 3 times the mass of the object on the right. So we can see that no matter what the mass, any two objects will have the same gravitational force towards each other. Can you feel Newton's third law in your spleen now? It should settle inside you and become a part of you.
I don't know about settling inside of you and becoming part of you, but you should have enough information now that you can do your assignment. The assignment is 4.7-12, so go look at that. It's about action and reaction pairs. It's having you identify what is pushing on what or what's pulling on what, and keep it simple. Remember, we're trying to describe the action and reaction forces, not the motion. Something pushes on something. something pulls on something. Keep it as simple as you can.